Hello, Philip Eaton here again. Welcome back to Vectrex Programming using Forth. First thing I wanted to do when I was looking at CamelForth was look at its memory map and see how it matches against the Vectrex. So on this page here on the left I've got the Forth memory map for CamelForth, and this was originally put onto what's called a ScroungeMaster 2 PCB or single board computer. I'm not quite sure. I've never seen one of these before. I can't find any information on the internet about it apart from what's with CamelForth, but nonetheless the memory map looks fairly straightforward. And then on the right here I've got the memory map from the Vectrex, which is also reasonably well known. Let's compare the two. So on the Vectrex memory map we can see that from 0 to 7 FFF, which is 32K or half the memory space, we've got reserved for game ROM, which basically means cartridge slot. So if you plug a ROM in, it could be, or a cartridge ROM, it will either be 4, 8, 16 or 32K of ROM, depending on whether it was one of the early games which are 4K or some of the later ones which are homebrew are 32K up to possibly even more than that with special bank switching, but let's not talk about that. So the first 32K on Vectrex maps to this region of the ScroungeMaster 2 memory map here. So what have we actually got in this memory map area? Well, the first 0 to 6000 hex is unused. Now 6000 hex is actually 24K, so that's most of the room there. 3/4 of it is unused, as it says. Now from 6000 through to 8000 hex we've got a mixture of RAM and onboard I/O. Now the ScroungeMaster has an 8K RAM which covers 6 through to 8000. That's 2000 hex, which is 8K of RAM, and the last part of it, 7C00 to 8000, is onboard I/O. So there must be some of that RAM, I guess, is not usable. It's mapped onto some I/O, and that I/O is actually a UART, and that UART is a serial port which allows communications to and from the device. So we've got almost an 8K RAM of use here, plus some I/O, whereas on the Vectrex we don't have RAM in that space. We have it somewhere else. We've got it at C800 through to CBFF. So the Vectrex has a 1K RAM and the ScroungeMaster 2 has 8K of RAM, and they're in different places. So that could be tricky. So what else have we got? So the Vectrex has got a PIA at DXX0 through to DXXF. So what that basically means is it's covering, it says 16 bytes here, but the way it's decoded in the address space, it means it takes up between D000 and DFFF, which is a 4K chunk, I believe. Where is that on the ScroungeMaster 2? Let's have a look. So we've got 8000 through to E1000, which is a great big empty space. It doesn't look like it, but it is. This is not linearly shown on here. These addresses are not linear. So a chunk of memory here between D and one below E, DFFF, which is a 4K chunk, has got the PIA on it, and we don't have that on the ScroungeMaster 2. Additionally, E1000 to EFFF, which is from there to there, is the Mine Storm ROM, whereas that's where the fourth kernel is on the ScroungeMaster 2. And between F000 and FFFF, which is there to there, we've got the Vectrex BIOS. So there's a load of clashes here. We've got the ROMs for the Vectrex are in the place where the ROMs are for the fourth kernel, and we've got 1K of RAM on the Vectrex, whereas Forth on the ScroungeMaster is using 8K of RAM, and we've got address space that's not used on the ScroungeMaster, which is where the Vectrex expects the cartridge to be. So they're quite different. So that would sound like quite a problem. Well, it might be, but hopefully not. So let's look a bit closer here. what I really want to do is to make this memory map fit onto the Vectrex, and I think it's doable, because there are parameters that allow this ScroungeMaster, or rather allows the CamelForth to be set up to fit the ScroungeMaster. It should be able to be set up to fit the Vectrex. The only question is whether or not it can fit the Vectrex, given that the Vectrex runs the Vectrex BIOS at boot, not Forth. So we have to try and work out if we can sort that out. Anyway, if we're going to compile Forth onto this memory map, let's see how we could do it. So firstly, the Vectrex has got 32K of ROM space available where it could put a program. Let's say that program is Forth, so we could start compiling Forth at 000 and it ends where it ends, which I happen to know is about 5K's worth of code for just the Forth operating system or program sets. Now this part here, as I mentioned, is an 8K RAM, and we've only got 1K on the Vectrex. However, if we look at the actual RAM that's used, apart from let's ignore this Forth dictionary for the time being, the RAM between 79880 and the top of here 7C, so that's, let's say it starts at 7900, so that's 9AB. That's actually 3 blocks of 100 hex, which is actually only 3/4 of a K. So this slot here requires 3/4 of a K, and that would leave 1/4 of a K for the Forth RAM dictionary. Or in other words, how many would that be? 256 bytes to put new Forth words in, or just use as variables. Now that doesn't sound like very much, but back in the 70s that would be loads. So actually this is doable with that tiny amount of RAM. So ideally it would have 6 through to 7,000 hex, which is 4K plus 9, which is about, I don't know, about 3K. So overall, on the ScroungeMaster, there's about 7K available for new programs, and we've got 256 bytes. But it's okay. It's the concept that's important, and it will fit. What else have we got? We've got a PIA, where we just don't need to tell Forth about that. We can just write directly to it. Because it's at D0, it fits in this group that's unused at the moment. So what we're going to end up with is a memory map that's got the Mine Storm and RUM at the top. We're going to have Forth at the bottom, and we're going to have some RAM in the middle at C8, where I'm going to fit all of this lot, and the PIA stays where it is. Now there's actually an option I haven't really considered here, and that is I could remove the ROMs completely from the Vectrex here and replace it with the Forth kernel, which would then allow me to use RAM all the way up to, well, up to C800 here, or I could put ROMs in there, or anything I want really. The whole thing would be under the control of Forth. I'm not sure whether I'll do that or not. I probably will not do that because there's actually quite a lot of spare address space on the Vectrex across the whole memory map. And additionally, if I did that, then I wouldn't be able to use the BIOS features that are available in the RUM, and anyone who was going to use my code would have to remove the ROMs from their own Vectrex and replace them with my ones, which I don't think is going to happen. So the chances are I'm not going to do that. I'll somehow try and wedge Forth onto the same address space as the Vectrex already has with its RUM and its Mine Storm. So here's one I prepared earlier. This is the CamelForth address space adjusted to fit onto the Vectrex. So as I mentioned earlier, we've got the Mine Storm and RUM here, F000 through to FFFF. That's 8K at the top of memory space. At the bottom of memory space, between 0 and 7 FFF, we've got the CamelForth ROM. We're only using about 5K of that at the moment, but we can put it there. And then big space between 8000 hex and C800, which is the same as here, nothing between 8000 and C800. Then we've got the sum BIOS Vectrex BIOS RAM through to C87F, which is here. I'm using the word RUM here. That is the original manufacturer's word for BIOS, I guess. They called it the RUM. Then between C87F and C880 is memory that can be used by the application. So that's where I'm stuffing all of the bits that are required by Forth. So I've got Forth RAM dictionary, which is 80 bytes. So that's not many. That's what's that? My maths are failing me. 128 bytes of RAM. I thought it was 256. It's not. It's less than that because you've got this RAM, RUM RAM also. So yeah, super tiny dictionary. Not putting many new words in there, but nonetheless it should work. Next bit is the TIB, which is a text input buffer. So when you type things using an interactive terminal into Forth, they go into there. 128 bytes. So if you type too many words, you'll have a buffer. You'll have an overflow of the buffer. Then you've got a user area. That's for temporary. Oh, what is user area? I'm not sure. I can't remember what that's for. Then you've got a parameter stack, which is where low-level words put their parameters between function calls. So if you're programming C and you want to pass some parameters to another function, this is where you do it on the parameter stack. Next down is a hold and pad area. This is for when you've got some of the Forth functions that do things like create some text strings. You need a bit of working area to manage your text string, and that's where it is, in the pad area. Then you've got a return stack. Excuse me. This is mapped to the user stack on the 6809. So Forth works out where the return is going to be when you do a branch, and it will store that information there on the return stack. Then you've got some BIOS housekeeping space, CBEA through to CBFF, which is where is that? BEA. Yeah, I've read that somewhere else. It's not listed down here, but nonetheless, there's some BIOS housekeeping area there. You've got a mirror of the RAM, so literally a duplicate of it that you can't use in that area. Then you've got the VIA that was already there, DXX0 through to DXXF. Some area that's do not use. I can't remember why that is. So there you go. That's the two address spaces mapped together. So I've got the RUM BIOS and Mine Storm up the top. I've got Forth at the bottom. And so what we need to do then is to make the Vectrex boot up into its own ROM and then run Forth effectively as a cartridge. And what Forth is then going to do is map all of its RAM areas, such as text input buffer, parameter stacks, return stacks, and its direct dictionary for new words, into this 1K address space we've got here. Sounds tricky, but in theory it should work. So we've mapped the address space of the Forth onto the Vectrex, but we've got some bits missing. So I mentioned that Forth has usually got an interactive prompt where you can type things in and it will respond to whatever you type. That's, at a very basic level, that's what Forth does. It waits for input from a keyboard and then processes it when you type it in. Now the Vectrex doesn't have a keyboard, doesn't have a keyboard socket or anything like that. All it's got is a programmable interface adapter, the PIA, and that's set up really for joysticks. We've got the two joystick ports on the front of the device. There isn't really one for a keyboard. Now you could put a keyboard on there, but even then you don't have a standard raster monitor which would operate in the same way as, for example, a Jupiter Ace or a Commodore 64. So whatever you type in, I've either got to make it work through the Vectrex monitor, or more ideally work on a separate screen. So the computer would be working with a raster screen and a separate keyboard. And that's how we did it back in the day with our single board computers. We had a serial port on the single board computer and would plug in a terminal via RS-232, which allowed us to type into the single board computer using a keyboard, and then it would send information back up that serial cable to your computer that the keyboard was attached to, and it would then display whatever it had sent, the single board computer had sent to you. And that really, I think, is the way that this Vectrex would need to work with Forth. So somehow I need to get an interface onto the Vectrex that is a serial port that can then support a terminal with a keyboard and a display. So if I'm going to put a serial port onto this device, where am I going to put it? Well, just like the VIA or PIA, I think it's the same thing basically. Yes. I need to find some address space to put it into. It's all looking quite congested up here at the top end of memory. But there's a nice big space here between 8000 hex and C800 with nothing in it. So what I could do is map it into that space. Now what I don't really want to do is put it right at the bottom of that space at 8000, which is probably the easiest thing to do from an addressing point of view, because it's a nice round number, easy to address, doesn't need lots of lines, not much control logic. But what that then restricts me from doing is having a bigger ROM. What I'd like to do is use as much space as possible, or have available as much space as possible to put bigger Forth programs. Because if I want to write a Forth program that's going to get big, I've got quite a lot of room here, 0 to 8000, that's that's 32k, and then there's another, what's that, 8 to C, 8, 9, A, B, C, it's 5 lots of 4k, so it's about 20k extra that we can map into there. So ideally, if I'm going to put a serial port anywhere in there, it's going to be right at the top end of this scale here, out of the way. So yes, I could put a serial port in there. Now what would that serial port look like? So let's have a look at Grant Searle's website, because he's already done this, sort of. He's designed a 6809 computer that has just 6 chips, or 5 if you're using a USB to TTL serial cable, which frankly everyone will do these days because it's very difficult to get an RS-232 port on a PC. So his computer is a 6809. It's running with a 7 meg crystal, which gives you a 1.8 meg clock, whereas I think the Vectrex is a 1.5 meg clock, so it's pretty similar. Again, he's using the first 32k for RAM, like the ScroungeMaster, although it could be ROM, doesn't really make a lot of difference. You've got from free space between 8000 and 9 FFF hex, which is another 8k, and then he's put his serial interface at A0000 to BFFF, which is a huge amount of room, which is what A and B, that's 8k of decoding. When you only, frankly, you only need 2 or 3 bytes, but it's easy to decode if you take a large amount of room. And then he's got some ROM between C0000 and FFFF, and this is what his circuit diagram looks like. So he's got a microprocessor, 32k RAM, 16k ROM, some very simple decoding logic so the processor can control these chips, as well as this one here, which is, if you can see the tiny text there, a 68B50, which is a UART or a serial port. And then this chip here is what's called a MAX 232 or equivalent, which takes the TTL levels out of this chip here and boosts them to a stronger level. I think they're about 3 to 5 volts coming out of the chip on TTL, whereas RS-232 is something like 20 volts or something like that. Don't quote me on that. And if you use a USB to TTL level converter, which most people do these days, he's got one. He's got the pin out for one here. You can take this chip out and plug this almost directly into your computer. So that brings it down to 1, 2, 3, 4, and all these NAND gates here are actually on one chip, U6. It's a quad NAND by the look of it, a 74LS00. So that's how he's put a serial port in there. So what I basically would need to do is take a 6850 here and then somehow map it onto my address space so it can be controlled in the same way that he's doing his. So that's how I will get a serial port onto the Vectrex. So I wouldn't use the joystick port, although I could do, potentially I could use the PIA and use something called bit banging, which is a way of simulating a serial data stream using well-timed code in the Vectrex, but frankly that's a bit messy. It's easier to just put a 6850 on there and be done with it. So that's probably the way that I will go. And so with those decisions somewhat made, that's the end of this little video. See you in the next one.